let's go ahead and get started. First of all, I wanted to address the question that we had last time about the problem with the derivative with respect to tau of t minus tau. I tell you guys, it was a hard problem. It was a lot harder than I anticipated. When I gave it, I thought, I could just knock this out really easily. But it turns out that indeed that's not the case. And in fact, I'm going to share my screen with you. And show you something. Okay, hopefully you can see my screen right now. But if you go to the homework, I put the solution to the problem right in the homework, so you'll be able to look at that at your leisure. So we'll be able to do that pretty easily. You'll be able to do that pretty easily, I suppose. One of the things that I avoided here is using any theorems. I found out that when I used a theorem, I thought, did I apply that theorem right? I didn't know, so I went back and I derived everything from scratch, only assuming the definition of the Fourier transform and the inverse Fourier transform. And guess what? Adam, you were right. The final solution does have an a squared in it. Remember I said that was against my intuition? Well, it does have an a squared, and in fact, it has a magnitude of a here. And I wanted to talk about that for a second. I don't believe, okay, what did I do with my pen? Oh, there it is. I don't believe that Google Docs lets me write on here. No, it doesn't. So I'll go to the slides then and talk about something which is important, which is when you use the magnitude of A, because I think this is a common misconception in Fourier analysis. So let me go ahead and try that. Let me go here, and this is kind of where we ended up last time with the jink, and I'll add a new page here. But the interesting theorem is x of at has a Fourier transform of one. This is not the transform of x of at. What I'm writing down here. This is a common mistake. Rather, it is, man, I can't be consistent with my A's. I have a mental disconnect here. Okay, rather, the proper theorem is that it's the magnitude of A. Now, this is not apparent in the derivation of the theorem of the scaling theorem, but the proof is a little bit tricky. You have to be careful about it. But the proof is that x of at has a Fourier transform of what? The integral of x of at e to the minus j 2 pi ut dt. And the integral is from minus infinity to infinity. Now, what one does is performs a variable substitution. In this case, the variable substitution would be of the form c is equal to at, which means that dc or dt is equal to 1 over a times dt. That's all well and good. And so if we make this variable substitution, we get the integral from minus infinity to infinity. Sorry, I don't like people yelling out equations as they write them, but I'm stuck with that. E to the minus j 2 pi u, and then instead of t, wait, where did I have dc? Or no, dt is equal to 1 over d. There it is, should be that. So t is equal to c over a times dt, which is 1 over a times dc. This, though, is not correct. This is only valid for a greater than 0. Why is that? Because we forgot to say if t is equal to infinity minus infinity, then that means that what I'm doing is I'm looking at these integration limits. If t is equal to minus infinity, then c is equal to minus infinity only if a is greater than 0. The same thing with infinity. T is equal to infinity implies that the variable is equal to infinity if a is greater than 0. What if a is less than 0? If a is less than 0, then this integral is wrong. Rather, we have to say if t is equal to infinity, then what about c? C is equal to minus infinity, right? If a is less than 0. And if t is equal to minus infinity, then that means that c is equal to plus infinity. And so we have the integral from infinity to minus infinity of the integral under the condition that a is less than 0, right? If a is less than 0, then the integration signs get flipped around. But if you recall, we can flip integration signs around if we do minus the result. And I'm not going to copy everything else down. I'm just going to do this. And with this minus sign here, we're integrating instead of, here we're integrating what? From right to left. We put the minus side, we're integrating from left to right. And what that does is it gives us it looks like I'm going to have to copy the whole thing down anyway. I'm going to put the minus sign with the a. But if the a is less than 0, this is exactly the same thing as saying the magnitude of a, isn't it? If a is less than 0, then minus a is the magnitude of a. So therefore, if we use the magnitude of a, it allows us to take into account both a is greater than 0 and a is less than 0. So that's the reason in the scaling theorem there's the magnitude here. It's a little bit tricky in the derivation, but that's what the result is. Is that okay?
Yeah, it occurred to me when you were writing dt equals 1 over a times dc that like the we're saying that the proportion between the sizes of the steps dt and dc is 1 over a, and we can just like take out the concern of the sign of a and just.
Well, I'm sure, David. Yeah, I'm sure, David. There's a number of ways of looking at this, and I'm sure that your way is valid. I totally don't follow it, but I shouldn't say I shouldn't say I totally don't follow it. I don't follow it totally. But I think it's I think you're probably right, and just like a lot of things, there's different ways to look at it. But this is the way that that I look at it. So therefore, make sure you use the magnitude of a in the scaling theorem. Okay, let's go on to some other interesting things about the Fourier transform pairs. Last time we defined the Jink, and we found out that the Jink was equal to the Fourier, or the inverse Fourier transform of a circle. In other words, that's what this is, 1 minus u squared. And it turns out to be a circle. Man, I'm doing terrible circles here, aren't I? It's going to be this is going to be the inverse Fourier transform of a circle, and I think we ended up there last time. Let's go on to one more Fourier transform pair, and something which is used quite a bit. This pops up a lot in optics, and that's the sine integral. And the psi of pi t is equal to pi times the integral of sine of t. Now, this is interesting because if I ask you to integrate the sinc of t, the sine of pi t over pi t, you thought, you know, I might be able to do that. Maybe integration by parts or something like that. No, you can't. And what happens in higher transcendental functions are like sines and cosines and Bessel functions and sine integrals. What you do if you can't solve something in closed form, you define a new function for it. And that's what this function is. So it's the integral of a sine, or of a sinc, I'm sorry. It's the integral of a sinc. And you can see it kind of oscillates here. And I think you can see that it kind of is a sloppy unit step. Well, not exactly a unit step since it doesn't go to 1, but it is, it does appear to have a discontinuity if we were to scale this down in some fashion. I'm going to stop sharing here because I'm not, and I'm going to share again because I'm not sure what happened to all you guys when I shared. Oh, okay. Here's what I need to do. Chat, pause recording. I don't want to hide the video channel. I want to see you guys. Where are you at? Can somebody help me where to go here? Okay,
Can you see yourself?
I'm showing the, oh, you know what? I put it down here. Look at that. Okay, I put it down. I hit it so well, even I couldn't find it. Okay, so this is where we are right now. So this is the sine integral, and you can see that basically the derivative of the sine integral is the sinc function. Now, in the book, there is a list of Fourier transform pairs. Now, these are functional Fourier transforms. I don't know if you can see this on your screen because the notation is so small. But here we have a number of functions of x of t and their corresponding Fourier transforms. And you can see a lot of these we have derived, a lot of them we have not derived, but there's a bunch of them which is in the book. There's a bunch of them which are in the book. And there's too many of them for one page, so we have another page of them. And we have things that we've seen before, like we have, for example, that a delta function Fourier transforms to 1, an exponential transforms to a complex exponential transforms to a shift. We didn't go over this too much, but it turns out a cosine transforms to 2 delta functions, and the rectangle function Fourier transforms to a sinc, and a number of other ones. We didn't derive this one, but this one is very easily derived, as is most of the other values in here. Some of the other ones aren't. Some of the other ones are more difficult to derive. But they are covered in the book somewhere, and this is one page of them. This is another page of them. And we can see that in some cases it isn't this simple. We didn't go over the integral theorem, but remember when you differentiated, you multiplied by j2 pi u, right? Well, when you integrate, guess what? In many cases you just divide by j 2 pi u. In this case, it's a 2u, but you divide by the corresponding j2 pi u, that shift. So here's another interesting one. How many know what a hyperbolic secant is? You've seen hyperbolic functions before. It's 1 over the hyperbolic cosine. And the hyperbolic secant, interestingly, is also its own Fourier transform pair. So we have a number of them, and then a number of cases we did not talk about. We did not talk about Chebyshev polynomials or Legendre polynomials or Hermite polynomials. So certainly that's outside of the scope of this class. So many of these things you're not going to be held accountable for. If you're interested in them, there are details in the book. Okay, the only thing that remains to do in chapter 2 is to, number 1, catch up on some of the theorems that we haven't talked about yet, and then talk about how all of this relates to the discrete time Fourier transform and the discrete Fourier transform. So let's do this. Here's an interesting property, and this is very interesting. So it says that if you want to look at an area of a function, you just have to look at its Fourier transform at the origin. This follows from the fact that x of u is equal to the integral corresponding to the Fourier transform. That's the worst D in the world. Okay, dt, right? So what I'm going to do is I'm going to set u to 0. If I set u to 0, this wipes out this entire exponential. It goes to 1, and we're left with the signal integral property. So this allows us to evaluate a number of interesting things. I mean, what's the integral from minus infinity to infinity of a jink function? To evaluate this, you'd have to go to Mathematica or Wolfram Alpha or something. But if we go back, let's see if we can find the jink function on here. Okay, I don't see the jink function here. Maybe it's here. Do we see the jink function?
Yeah, it's the 5th.
Okay, yeah, here we go. Okay, the jink function was the circle, right? The jink function was the half circle. So therefore we could go back to here and we could say this is equal to that's the Fourier transform, and then we evaluated at u is equal to 0. So we immediately conclude that we can integrate this Bessel function sort of thing by looking at this at the origin, and it turns out to be 1. So that's the integral of the jink function. So we see we can apply this to any time we have a Fourier transform pair and want to know the area under a signal. Sorry. So that's called the signal integral property. This is very interestingly because it means that if you have any finite energy signal, that the integral of a derivative of a function is always equal to 0. Why is that? Because if we set y of u is equal to j2 pi u x of u, if you remember from the derivative theorem, this means that y of t is equal to d dt of x of t, right? That's the derivative theorem. What this says, interestingly, is that the integral from minus infinity to infinity of y of t is equal to y at 0. So that's equal to j 2 pi u x of u, evaluated at u is equal to 0. And as long as x of u is finite at the origin, then this u goes to 0, and the result is 0. So the derivative of any function, of a finite energy function, has the interesting property that the integral from minus infinity to infinity of the derivative is always equal to 0. Kind of an interesting result, right? A little bit unexpected, I would say, especially if you haven't seen it before. So that's the signal integral property and one of its interesting manifestations here. Let's look then at other properties. One is conjugate symmetry of a real signal's spectrum. A Fourier transform of a real function is conjugately symmetric. Some people refer to this, and you'll see this in the literature sometimes, as a Hermitian property. Because of the great mathematician Hermite. He has a bunch of stuff named after him, including some polynomials, the Hermite polynomials. Well, this means that x of u, one of the things this means is x of u, if we take the magnitude of both sides, is equal to x of minus u. Therefore, if you see Fourier transforms and you see their magnitude plotted out, the magnitude of a spectrum, you will always notice that that spectrum is an even function. The magnitude of the spectrum is always an even function. We'll say more about that in a little bit. But the other interesting thing, it kind of answers the quandary about what the heck is negative frequencies. This property says that if you have real signals, and by the way, all the signals we deal with in reality are real, right? Otherwise, they would be imaginary, and imaginary things don't exist. So all of the signals that we deal with are real. And so all real signals have this conjugate symmetric property. It's kind of like being even, except that instead of just flipping around and getting the same thing, you flip it around and do a complex conjugate, and then you get the same thing. So it's a generalization of the even function in a way. Well, this tells you something interesting. If you have, for a real function, if you have the positive part, if you have a positive part of a spectrum for positive frequencies, then that's all you need to know to totally define the entire spectrum. Why is that? Because you can flip it around and you can conjugate it. And if you flip it around and you conjugate it, then that is the negative frequency components of the spectrum. And this is true for all Fourier, this is true for all real signals. The proof is pretty straightforward. Let me go ahead and show it to you. It starts out like everything does with the definition of the Fourier transform. And now we're going to conjugate it. Conjugation, if you remember, mechanically corresponds to just setting all of the j's equal to minus j's. Now, because this signal is real, once we conjugate it, we get the same exact thing. So it doesn't change. We conjugate it, we get exactly the same thing, correct? So we get exactly the same thing, except this minus j becomes a plus j. And the last thing we have to do is we have to look at the conjugate of the result and look at minus u. And we see that, well, we get the same thing here. Except that guess what? This u becomes a minus u. That u becomes a minus u. Whoops, forgot my e here. And we're back to the original definition of the Fourier transform. So all real signals are conjugately symmetric. If you flip them around and you conjugate them, you get exactly the same thing. And it answers the question, what do we do about negative frequencies? Well, if we know things for positive frequencies, then automatically, if the signal is real, which it is in the real world, then we know that the negative frequencies are going to be determined by the positive frequencies, by the flipping and the conjugation. This has interesting properties because if this is true, x is equal to x conjugate of u, and x, any complex signal can be written as its real and imaginary components. So r of u is the real part, r of u is the real part of x, and I of u is the imaginary part of x. So notice what happens. X conjugate of minus u must be equal to r of u, r of minus u, minus j times the imaginary part of minus u, right? Now what we need to do, anytime we have two functions that are equal to each other, and we know that these are equal to each other, we know the real parts and the imaginary parts must equate, correct? So equating the real part, we get that the real part of the Fourier transform is equal to r of minus u. So equating the real part, we find that the real part of a Fourier transform of a real function is an even function. Likewise, if we equate the imaginary parts, we get I of u is equal to, we have to take into account this minus sign here, minus I of minus u. So it turns out that the imaginary part is always odd. So the real part is always even, and the imaginary part is always odd. This is true of a Fourier transform of any real signal. And you might have fun. Go back to the table and look at a few of the Fourier transforms, and you can convince yourself that this is true. Because if you look at the Fourier transform, yeah, the real part is an even function and the imaginary part is an odd function. We could do something similar. We could do something similar with the magnitude and phase. Any complex function can be written as its magnitude times e to the j raised to its phase. And we'll use this angle notation here to correspond to the angle of x of u. Now, if two functions are equal to each other, this, by the way, is equal to x of u times e to the minus j angle of x of u. Because we know that the function is equal to its conjugately symmetric version. So we can put this in here. Now, if we take the magnitude of a complex signal, it doesn't matter where the conjugate is in there or not. The only thing that really matters is the minus j here. So if two functions are equal to each other that are complex, we have to have the magnitudes equal to each other, and we have to have the phases equal to each other. So the magnitudes must be equal to each other. So therefore, this must be equal to this. In other words, the magnitude of the Fourier transform of any real function is an even function. Likewise, we have to equate the phases. If the phases equate, we have that the phase of the signal is equal to minus the phase of the transpose of the signal. So therefore, the phase is always an odd function. So this is, I think, an interesting property also of the Fourier transform of real signals. Again, the magnitudes are even functions and the phases are odd functions. Next, we're going to choose the power theorem. This is enormously important, and especially if you go into quantum mechanics, this relationship is used all the time, because in quantum mechanics notation, you might have heard of caret sort of notation. This is kind of the shorthand notation for X, Y. Anybody taken quantum mechanics and seen notation of this sort? Okay, so it's something which is used a lot in quantum mechanics. So let's take a look at this. And what it says, if you multiply a signal by the conjugate of another signal, that's the same thing as in the frequency domain, taking the signal and multiplying it by the conjugate of the signal in the frequency domain. This is very useful because it allows us to flip back and forth between the time and the frequency domains and still do similar sort of operations. And the proof is pretty simple. By the way, all of these proofs, I don't know if you've seen these proofs very much off and on, but all of them are pretty straightforward. They just correspond to use of definitions, manipulations of variables, and uses of previous theorems. So that's what we're going to do here. First thing we're going to do is, instead of x of t, we're going to put into x of t, we're going to use this inverse Fourier transform. Now I have to be careful here. I can't use u because let me use v. Or nu. Or maybe I don't need to. No, I don't think I need to. I'm going to go back. I'm going to change my mind. I'm going to call this u. Let me rewrite it. The next thing I'm going to do is I'm going to change the order of integration. If you recall in this course, when can you change the orders of integration?
Always.
Always, that's right, anytime you want to. So I'm going to change the order of integration. So here my integral is over u, here it is over t. So I'm going to first of all do my integration over u. And then I'm going to do my integration over t. Let me do that backwards. Hopefully I slipped that in there before it fell off the screen. So I've switched the order of integrations. And I get x of u. And I'm going to take everything in this bracket and I'm going to conjugate it. In other words, I'm going to talk about y of t and e to the minus j 2 pi ut. Went a little off the reservation there. You see what I did? I took this conjugate outside so that I could conjugate everything inside. So y conjugate of t became y of t, and the e to the plus j became e to the minus j. And look what we have. What we have in the bracket is the Fourier transform of y. Except for the bracket, it's conjugated, isn't it? Because of the bracket, it's conjugated. So therefore, we see that the bottom relationship here is equal to the top relationship. And that was what it was promised in the Power Theorem. Any questions? We're going full steam ahead here. Okay. Hearing none, let's go on to a special case of the Power Theorem that we use all the time, and this is incredible. And that's Parseval's theorem. Parseval's theorem says this. We've already seen Parseval's theorem. Parseval has a bunch of manifestations of his theorem. It relates the energy in one domain versus the energy in another domain. We've already seen this for the Fourier series. There's an equivalent here for the Fourier transform too. And it says that the integral of the magnitude squared of a function is equal to the integral of the magnitude squared of the function in the frequency domain. Do you remember what this is from our signal classes? This is the energy of the signal. That's equal to the energy of the signal. Therefore, what we're saying is that the energy of the signal in the time domain can be computed, and it's exactly the same as the energy if you go to the frequency domain. Again, I point out because if you were to, I like to point this out occasionally. We're using U, remember cycles per second instead of radians per second? If we were using radians per second, there would be a 1 over 2 pi or a 1 over 2 pi squared here, I forget. But because we're using just cycles per second, there's no 1 over 2 pi to mess things up, which is very nice. And you can see this is a special case of the Power Theorem by setting y is equal to x. Right? If we set y is equal to x, we know that x times x conjugate can be written, that's the definition of the magnitude of x squared. Right? From complex arithmetic. So setting y is equal to x, we get Parseval's theorem, which is a special case of the Power Theorem. Let's go on to a really, I think this is one of the neatest theorems in Fourier analysis. It's something called the Poisson Sum Formula. It can be looked at as a manifestation of the sampling theorem. It can be looked at as a manifestation or a generalization, if you will, of the Fourier series. It's just a very powerful way of doing things. Let's interpret it. Here's the equation. Look at it a second, and then I'll explain what it means. It says that if we have a replicated signal, x of t minus nt, what does that mean? That means if we have a signal x of t, say the signal looks like this. And then we take intervals of t. These are the intervals of nt, if you will. So this is n is equal to 1 This is n is equal to 2, n is equal to 0, n is equal to -1. And what we're going to do is we're going to take our cookie cutter and we are going to replicate this signal all down the axis. I'm trying to draw exactly the same signal just being replicated all over the place. Does that make sense? And then we multiply it by t. And then what we do is we add all these functions together. Now, I think you can see that if we add all these functions together, I'm not sure exactly what we get, but we're going to get something maybe that looks like this dashed line. We are going to get something which is periodic. We're going to get something which is periodic. But unlike the Fourier series, we're used to thinking of a period of the Fourier transform as being defined in a finite interval, so the cookie cutters don't overlap. But here we're allowing them to overlap. But nevertheless, we still get a periodic signal, even though the replications overlap. So if we multiply this by t, we obtain this result. We have seen that if we Fourier transform a periodic function, we get a number of Dirac deltas in the frequency domain corresponding to the fundamental and all the harmonics of the Fourier series. And that's exactly what we are saying here, that this, well, if we were to inverse Fourier transform, this is exactly the same as Fourier transforming a single period. See if this rings a bell. We Fourier transform a single period. We Fourier transform a single period, whatever that looks like. And then we sample that at intervals of 1 over t. If we sample that at intervals of 1 over t, we get the samples x of n over t. That's the conglomeration of the samples, right? And what we're saying is that if we take a single function, a single kernel of this periodic replication, we Fourier transform it and we sample it, this then becomes a component of something which looks like this. You know what this is? That's nothing more than a Fourier series, isn't it? That's nothing more than the Fourier series. These are our Fourier series coefficients we used to call C sub n. It's a Fourier series. So we're saying that you can take one of these kernels that we're replicating, we can take the Fourier transform of it, we can sample it, and that becomes the Fourier series coefficient. Now, the interesting thing is that the Fourier series is a special case of this, isn't it? For example, if we were to look at a Fourier series like this, x of t would just be this triangle at the origin, correct? And then we would replicate it out by intervals of t. As we saw before, we could take a single period of this. We could take a single period of this. We could Fourier transform a single period. We could sample it, and that became the Fourier series coefficients. So this is a generalization of that idea. And it's called the Poisson Sum Formula. Next thing I did want to talk about is, well, yeah, let's go ahead and talk about this. This is the LTI frequency response theorem. This is not in the book. I suspect it should be. This is very interesting. You all know about LTI systems. You remember them from undergraduate education, right? undergraduate case. Linear time invariant. That means it's linear, it satisfies the properties of homogeneity and additivity. It is shift invariant or time invariant. In other words, if you do it today, the system responds the same if you do it tomorrow or if you did it yesterday. The system itself does not change. If the system itself does not change, you have a time invariant sort of system. Linear time invariant systems are really, really stupid. They have no creativity at all. And if you tickle them with a sinusoid, they only respond with sinusoids. I remember living in a dormitory, which was in a large modular building at my undergraduate alma mater, Rose-Hulman. And I had an amplifier, a Vox Super Beetle, and we turned up the tremolo. And we started to go woo 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 woo, and you went up to the third floor and you put your hands on the wall and you heard a woo 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 woo. Guess what? The vibration was exactly at the same frequency as the amplifier down below. The building itself was a linear time invariant system, and it had no creativity. It couldn't create frequencies. The only thing it could do is replicate frequencies and attenuate them and maybe change the phase of the signal. That's all it can do. That's all linear time invariant systems can do. They can take a sinusoidal response and they can replicate the sinusoidal response exactly at the same frequency with a different magnitude and phase. That's the reason we use phasors, right? Because what do phasors do? Phasors keep track of the magnitude and the phase of the sinusoid in the circuit. Phasors keep track of two things. And with the linear time invariant systems, that's all you need to know. And the interesting thing is that if you have a linear time invariant system and you stimulate it with a sinusoid, it's going to respond with the sinusoid, just like it did in the building. Usually you see this as follows. You usually see it as h of t convolved with e to the j 2 pi nu t. It should be a convolution. Usually we think of this as the impulse response of the filter. You remember this? And here, this is going to be the input, x of t. So we're going to have x of t be a sinusoid, which is the input. And here's the cool result. If we take this x of t, this sinusoid, and we put it into this linear time invariant system with an impulse response of h of t, guess what we get out? We get out exactly the same frequency. We get out exactly the same frequency, except that it is altered in frequency, not in frequency, it's altered in magnitude and phase. And we call this h of nu. And this h of nu is referred to as by a number of different names. I like to think of it in terms of the frequency response. This is the frequency response of the system at the frequency nu. And to show this is very interesting. Watch this. H of t convolved with e to the j 2 pi nu t. If we write out the integral, we get h of tau times e to the j 2 pi nu t minus tau. Isn't that what the convolution integral becomes if we do convolution? This is x of t minus tau. Notice that we're integrating with respect to tau, so we can suck out part of the integration here. We can suck out part of the exponential, and lo and behold, yes, indeed, we get the same frequency out, except its magnitude and its phase is determined by this thing, which you'll notice is the Fourier transform evaluated at the frequency nu. So this is the frequency response, LTI frequency response theorem, that if you take any signal and you convolve it with e to the j2 pi nu t, usually I think of nu as a single frequency. If you take this input and you put it into this system, you get out of x of nu times exactly the same frequency. So linear time invariant systems are not very creative in what they do. Let's see. So we can apply the Poisson Sum Formula. We can apply this theorem, the derivative theorem, to the Poisson Sum Formula to derive the result. I'm not going to do that today because I want to take some time to answer any questions which you might have over the homework, because I would like you to hand it in Monday. I wanted to see how you're doing on it, whether you had any questions, whether you think you need more time. What's the situation? Hopefully you've had a chance to look at it, right? Let me put them up in order for you to have a peekaboo here at it. Okay, let's look at problem 8. Do you think you have a good handle on problem 8?
I have a question about it.
Sure.
So the Fourier series coefficients, I think you answered it during lecture, but those are basically just samples of the Fourier transform, right?
The Fourier coefficients, it's samples of the Fourier transform of a single period, yes.
Okay. And so I'm guessing there's different approaches to that, but I was thinking if that's true, then I can approach the problem that way. And so if you want to, are you basically asking for a new formula for the coefficients if we're looking for the derivative instead of I
want the new coefficients in terms of n. In terms of c sub n. It should be a function of c sub n. Now, what happens if you differentiate that one period? What do you do to the Fourier transform?
You multiply it times whatever it is, e to the whatever the derivative theorem. Whatever the derivative theorem is.
J2 pi u. And so you sample that. So the u becomes like an n over cap t, an n over the period. That's it. Okay. It's that simple.
Okay.
So
that's what I was thinking.
Yeah, you're totally right in your assessment, Aiden. Yeah.
Thank you.
What are the Fourier series coefficients of x of t over a? In other words, you have a periodic signal. And now you take and you stretch that signal. It's kind of like the time axis is a rubber band, and with it being thumbnailed at the origin, and you stretch that function out. It's still periodic. It still has the same shape. What about the Fourier series coefficients? When I first saw the answer to this, I was kind of surprised. Anybody have an idea what they are?
It should be the same, right?
They're exactly the same. Because the only thing that changes in the Fourier series is the e to the j stuff. All of the other stuff stays the same or can be variable transformed to be exactly the same. So the Fourier series coefficients of the magnified version are exactly the same as the original version. And that's kind of cool. That's kind of surprising. So you need to show that in your solutions. Now, number 9 is a problem that I gave you, which is going to require you to read the book. The answer is in the book. And I'm wondering if anybody has any questions about that now that I've given you the big hint. Did anybody find it in the book prior to this?
I found it.
Okay. So the answer is in the book. And isn't that interesting? If you have a causal signal, then what do we know about the Fourier transform of any real signal? Well, let's see. It's real and it's real parts even, its imaginary parts are odd. But this says if the signal is causal, not only that, you only have to know the real part of the signal. That you can get the imaginary part by taking a Hilbert transform. So this is very interesting. If you want to know the spectrum and it's a causal signal, then all you need to do is to compute the real part of the Fourier transform. If you have the real part of the Fourier transform, you can take a Hilbert transform, get the imaginary part of the transform, and that's it. And plus, you only need to know the real part of the Fourier transform for positive frequencies, don't you? So this really shows that there's a lot of redundancy in many cases in the Fourier transform in terms of its definition. I think it's a very interesting result. Okay, derive the Fourier transform of t e to the minus t squared. Anybody do this? Anybody know the approach that you should use to do this?
I'm guessing you should start with the definition. That's what I was thinking I should do, but I haven't done it yet.
Well, yes, I think you could, because the t is actually an integrating factor, if you remember from calculus. You could do it that way. I submit there's probably an easier way to do it, and that is from the derivative theorem. What happens if you differentiate a signal? What happens in the frequency domain? You multiply by u. What happens if you differentiate in the frequency domain? What do you do in the time domain? You multiply by t. Minus j2 pi ut, or minus j2 pi t. So the duality theorem again says you differentiate in time, you multiply by j2 pi u in the frequency domain. The dual of that is if you differentiate in the frequency domain, you multiply in the time domain by a minus j2 pi t. So I think that that's probably the easier way to do it. But Aidan, no, you're right. You can do this directly. It does turn out, I believe, that the t is an integration factor here that allows you to perform the operation. But I think that the derivative theorem approach is maybe more easily understood. Anybody get number 11? Simplify the expression for pi of t times the comb of, or convolved with the comb of t. Well, I'll let you stew on that one a little bit. The outcome is surprisingly simple. You might be able to do it in your head. And you might be able to do it in your head if you think geometrically. I really like thinking geometrically in this case. What happens if you convolve something with a delta function? If you convolve something with a delta function, you get the something centered where the delta function is at. So the comb is a replication of delta functions. So maybe that should tell you what that's like. Number 12, derive the Fourier transform of the first one, a triangle function times a rectangle function. Now, a triangle function is like this, right? It's kind of a pyramid. If you multiply it by a rectangle, you only get the top of the pyramid, then it comes down. Now, this will require you to apply some ingenuity that you haven't applied yet. And there's a very, very easy way to do this. Does anybody see what the easy way to do this is? If not, you'll think about it this weekend, won't you?
I might be crazy here, but since...
Yes, you might be crazy, Adam. Yes, okay, yeah, it might be.
But the rectangle function, since it just has a height of 1, wouldn't it just simplify to the triangle function?
Say that again.
If they have the same width, which I can't remember the definitions of how the widths work out, but
okay, the triangle function goes out to 2. I'm sorry, goes from -1 to 1.
Okay.
And the rectangle function goes from -1/2 to 1/2.
Oh, okay.
So
not quite the same.
it takes the triangle, and when you multiply the two, it looks like a house. You get the roof and then the sides.
Okay. So that's a bit different. Okay.
Yeah, so it's not just a triangle function. Do you want a hint? It's one of these things, once you see it, it's one of these flat forehead experiences. You go, oh, okay. Fourier transforms are linear, aren't they? Fourier transform of the sum is the sum of the Fourier transforms. Correct? Can you think of two functions that would add together that would give this house? Two simple functions.
Guess a scaled triangle and a rectangle, a scaled rectangle.
A scaled rectangle and a what? A scaled triangle, do you say?
Yeah.
Yeah, exactly. Think of it. It's this. Can you guys see me in my little window here? Okay, so
Yeah.
it's the house. So it is the Fourier transform of the base, which is what? A rectangle, just like David said. And the top, which is what? A little triangle. So it's a little bit different approach than you've looked at before. Then it says derive the Fourier transform of t times the triangle function. Again, I would ask you to look at the derivative theorem, because you're multiplying in the time domain by t, you kind of differentiate in the frequency domain. Same thing with 13, right? What's the Fourier transform of the jink? The Fourier transform of the jink is that circle, half circle. And if we were to differentiate that, that would differentiate that half circle in the frequency domain. That would be corresponding to multiplying by t in the time domain, or minus j2 pi t. Now notice, because of duality isn't exactly the same. It turns out that the derivative theorem says if you differentiate, you multiply in the frequency domain by j2 pi u. If you differentiate in the frequency domain, in the time domain, you multiply by minus j2 pi t. So there's a little bit of duality shenanigans that one has to do in order to apply that. And then the last question that I asked, hopefully these are enough suggestions to get you going. Does anybody have an idea of equation 14?
This one's kind of, I don't, like the cone function itself is already, it's just a shifted, you add up a bunch of shifted deltas. So I don't see how adding another shift really changes anything.
Aiden,
The definition of the cone function is already from negative infinity to infinity.
You're exactly right. We have a shift. We have a bunch of delta functions, and if we shift them over a period, in this case 1, we get exactly the same thing. Your intuition is exactly right. Now, it's interesting. This is a little sanity check. If you apply the shift theorem to that, you should get exactly the same result, shouldn't you?
Yeah, you should.
You should. And so your intuition is correct, and the answer is right. Just look at it from the shift theorem point of view and see if the shift theorem works here, or maybe it breaks. I'll give you a hint, it works. But it's just kind of fun to see the way that these things fall out. Very interesting. Now with that also, whoops, wrong one. No, that's okay. I also gave you some review problems from chapter 2. Yes, we're still in chapter 2. You can see there's a lot there if we really want to get our tool chest correct. I'm wondering if anybody has any questions about the review problems in chapter 2, even if you've looked at them. Yeah, I'm sorry, even if you haven't. Yeah, hopefully you've looked at them, even if you haven't looked at them. Yeah, please let me know. By the way, I think I've decided to have our first midterm after we're finished with chapter 2. So we're going to finish with chapter 2, and then I'd like to schedule an oral midterm with each one of you for about 10 to 15 minutes, and just kind of see, chat with you and see where you're at in terms of the material. I found out that oral examinations are really effective in letting me know where people are at. So that's a good thing. So if you've been slacking, now's a good time to start accelerating so that when the oral examination comes up, you'll be prepared. Okay, with that, are there any questions about anything?
Yes, I have a question. You said you would like us to turn the homework on Monday, but I think on the spreadsheet it says September 15th, which is Tuesday. So which one is it?
Okay, which one would you prefer?
Tuesday.
Tuesday. Okay, we'll do Tuesday. And this will be fair game for questions on Tuesday then. Maybe we should do that. Maybe we should have it due on Tuesday so that you are able to ask questions on the day that it's due and we can address them. But I don't want you to wait till the last minute. You're not going to learn this stuff. The thing with the Fourier analysis, and I hope you can see from the book, that you need to read the book, and you can't, it's not bedtime reading, right? You can't take the book to bed and just look at it. You need to sit down with paper and pencil and go through things. I was motivated in writing the book by the classical approach made by Athanasius Populus, who wrote the first book in Fourier analysis, I believe in 1965. And it was a mixture of rigor and intuition. In other words, I think everything we've done is rigorous, but I don't think the mathematicians would say rigorous. So I think it's rigorous from an engineering point of view. I think it's very intuitive from an engineering point of view. And I want to make sure that I wanted to make sure that I wrote the book that way. So Populus's book was called Probability and Stochastic Processes or something like that. There was another book by Ron Bracewell, I believe he was at Purdue, called the Fourier Transform. And his book was also written at that same sort of level to allow engineers to have good access to Fourier transforms without being buried in all of the mathematical detail. And believe me, you might think that we have a lot of mathematical detail, but compared to what the mathematicians go through in switching integration signs, making sure things are absolutely convergent, and going into measure theory and things like that, we're nowhere near that. And I think to teach this class at the rigor of mathematics would take, I don't know, 2-3 years. So we're not going to do that. We're going to proceed with this intuitive way that electrical engineers and physicists have used. And so I hope that that's acceptable to you. Any additional questions that you have? Okay, well, good. David slips his foot in the door at the last minute. Okay, David.
Yeah. You go over problem 13 again?
Again? Okay, let's.
I missed.
Okay, I'm going to share my screen. And we're going to go through problem 13. Is that the one you want?
Yes.
Okay. here is the basic idea. The basic idea is that we know from whoa. I got a skid marks there. That we know that the derivative of a signal Fourier transforms to J2 pi u times x of u, correct? The dual of that, remember, if anytime you have a Fourier relationship, you can flip it around by the duality theorem. The dual of that is if you differentiate in the frequency domain, this again is a derivative theorem. This is the dual of the derivative theorem. Then the duality theorem says minus J2 pi t x of t. So here you differentiate in time, J2 pi u in the frequency domain. Here you differentiate in the frequency domain, minus J2 pi in the time domain, correct? Then since Fourier transforms are linear, you can take this over to the other side. So you can take this minus J2 pi and you can divide both sides by it since the Fourier transform is linear. So I hope that helps. Okay, I see your head nodding. From agreement as opposed to sleep. Okay, good. Okay, any other questions? Last call. Okay, thank you very much, guys. We will see you next Tuesday.
Right.
Thank you. Bye.
Thank you.